Welcome to Algorush. Okay, let's just dive right in. Think about the massive data systems that power pretty much everything we do. Every single transaction, every little status update, it's a tiny edit. So how do these systems handle millions of them every second without just grinding to a complete halt? It's a huge fundamental challenge in modern computing.
So, to really get the solution, we've got to talk about the problem first. The foundation for a ton of these systems are classic data structures like B-trees, and they're super reliable. They've been around forever. But when you put them under the immense pressure of today's workloads, man, you start to see some serious cracks show up. And this right here really gets to the heart of it. We've got two massive bottlenecks. First up, there's this thing called write-amplification. This means if you need to change just one tiny detail, a traditional B-tree often makes the system rewrite an entire huge page of data. It's literally like rewriting a whole page in a book just to fix a single typo. Then you've got concurrency. When a bunch of users are trying to make changes at the same time, the system uses latches, and you can just think of them as locks, which create these huge digital traffic jams, forcing everyone else to wait in line. So what's the fix? Well, this is where the B-tree comes in. And it is an incredibly clever evolution of the B-tree, designed specifically to get rid of these bottlenecks with a totally new, and this is key, latch-free blueprint. All right, so what's the big idea here? The absolute core innovation, the real aha moment, is separating the logical idea of a node from its actual physical location in memory. The blueprint analogy is perfect. The blueprint tells you what the house looks like, but the bricks and wood can be stored anywhere. And that one simple idea, it changes the whole game. Okay, so how does this whole separation thing actually work in practice? Well, the first part of the puzzle is how the B-tree handles updates without those crazy inefficient rewrites. And it's all about something called delta chains. Now, to make this whole thing tick, the Buzzword-Tree leans on this really powerful, really low-level tool, a CPU instruction called compare and swap, or just CAS. And this, right here, is the secret to going lock-free. It lets the system check a value in memory, and if and only if it hasn't changed, update it in one single uninterruptible step. It's like a surgeon making one precise move, and it's all over in an instant. So with CAS in its toolkit, the Buzzword-Tree does something brilliant. It never overwrites old data. Instead, when a new update comes in, it just creates a little delta record for that change and slaps it on the front of an edit history chain. The sticky note analogy is perfect. You're not erasing anything, you're just adding a new note on top. It's so much faster, it's cleaner, and it totally avoids those traffic jams we talked about. And you can see exactly how it works right here. It's actually pretty straightforward. You've got your original data, the base node. Then, boom, an update comes in. That's our delta node. And then, using that super fast CIS operation, the system links that new delta right to the front of the line. And that's it. The update's done. No locks, no big rewrites. Simple. Okay, but hold on. You're probably thinking, if we're just throwing these new delta nodes all over memory, how on earth does the system keep track of it all? Well, that brings us to the second piece of magic, the logical mapping table. Think of it as the system's central address book. Yeah, this table really is the secret sauce. All it does is translate a permanent logical ID for a node into wherever that node happens to be physically located in memory right now. So when the system wants to find node number L101, it doesn't have to hunt around. It just checks the table, gets the address, and it's there. This is what makes the whole logical physical separation possible. And the power of this indirection is just immense. It means the system can shuffle the physical data around for whatever reason, maybe for optimization, and it doesn't matter. Nothing breaks because everyone is still pointing to that stable, logical ID. I love this analogy. It's like telling a friend to meet you at the post office instead of giving them an address. If the post office moves to a new building, your directions are still good. All right, so we've got these chains of edits growing and this cool mapping table that lets everything move around. But yeah, you have to be wondering, what happens when that chain of sticky notes gets ridiculously long? The system's got to have a way to tidy up, right? You're absolutely right. If you just let those deltas pile up forever, performance is going to tank eventually. Imagine having to read through 100 sticky notes just to find the current piece of info. No good. But of course, the Buzzword-Tree has a really elegant solution for this too. Basically, it handles two key jobs in the background. First, there's consolidation. Every so often, the system just grabs a base node and its whole chain of deltas, squishes them all together into one brand new, clean base node, and then just updates the mapping table to point to the new location. Easy. And second, garbage collection. Once it's sure that nobody is looking at the old base and delta nodes anymore, a safe process comes along and reclaims all that memory so it can be used again. So let's put it all together. You take the delta chains, the mapping table, and these cleanup processes, and what you get is a data structure that is just perfectly built for the kinds of high concurrency workloads we see everywhere today. So let's wrap this up and talk about why this is such a big deal. Let's bring it all the way back to those problems we started with. The B-tree just tackles them head on. That write amplification problem, it's way, way smaller because we're just adding tiny deltas, not rewriting huge pages. And what about concurrency? It's through the roof, because using compare and swap means we can just get rid of those slow blocking latches. The whole thing is just perfectly tuned for modern multi-core CPUs that are great at these atomic operations. It's an elegant fix for all those cracks in the old foundation. And this leaves us with one final big idea to chew on. This concept of separating the logical structure from the physical implementation. It's just so powerful. You see this pattern pop up all over the place, in virtual memory, in networking, and all kinds of high-performance systems. So it makes you wonder, right? Where else can this exact same way of thinking unlock